Okay, hi everyone. So welcome to this parallel session on flat holography. We start off with Tim Adamo, and he'll tell us about celestial chiral algebras. Over to you.
Okay, thank you, and thank you all for coming. I am indeed Tim Adamo, but first things first, I just want to do a kind of forward advertisement for the rest of this week. There are, believe it or not, 3 parallel sessions on flat holography, and flat holography, of course, means many different things to many different people. We've heard a kind of great overview talk this morning from Laura about maybe shall we say 2 approaches to this, but of course there are many other approaches, at least in principle, and so all week we'll be hearing lots of exciting stuff about this. So if you're not buying what I'm selling, it doesn't mean you shouldn't keep coming to these parallel sessions. So anyway, today I'm going to focus on one particular aspect of one particular approach to this idea of flat holography, which is something called celestial chiral algebras, or if you like, chiral algebras in the context of celestial holography. So at least for argument's sake, let me pretend that maybe you haven't drank the Kool-Aid and these words don't necessarily mean anything to you. So what are these things? Okay. So again, Laura's done a lot of the heavy lifting for me already, giving you some kind of nice sales pitch for what celestial holography is. But let me give a very non-technical description of what's going on with this celestial holography program. It's this pipe dream that there's some sort of conformal field theory living on the sphere of null generators, whose correlators compute S-matrix elements, or at least massless S-matrix elements in asymptotically flat spacetimes. So this is supposed to be some sort of asymptotically flat holography. And this is, of course, a very ambitious pipe dream. But I want to just emphasize that, okay, if you're a gritty realist, like me at least, these sorts of pipe dreams can maybe be off-putting for you. People maybe taking a victory lap they haven't earned yet. But I want to emphasize that in real money, what's actually going on with this celestial holography program is typically much more concrete, or you could say much less ambitious, but there's kind of serious concrete things that one's talking about here that a priori don't necessarily have anything to do with this pipe dream, but are more about leveraging the power of conformal field theory to learn something about scattering in asymptotically flat spacetimes. So these celestial chiral algebras are what you could argue has been one of the key outputs of this celestial holography program over the last few years. And again, Laura has done a great job of setting the groundwork for me here, so I'll be slightly sketchy about this. But the key observation is that if you take the positive helicity soft sector of general relativity, and what do I mean by this? I mean kind of if you had a Fourier basis of positive helicity linearized graviton perturbations, and you computed S-matrix elements involving these guys, and you expanded them to all orders in the frequency, that's what I mean by the set of positive helicity soft gravitons, that these things form an algebra under collinear limit. And this algebra, if you hit it with a hammer and redefine the generators enough, takes this remarkably simple form. And the generators of this algebra, these things we call GM, GPM, R, these are just some rewriting of a basis of positive helicity soft gravitons. This mode number P, you should think of it as kind of telling you where in the soft expansion this generator is coming from. M is kind of, okay, we're in 4 dimensions, so the gravitons, you can think of them as parameterized by a null vector, and this is like 2 SL2 spinners. So one of them you can think of as a kind of SL2R bar, and M is telling you kind of the weight in that anti-holomorphic SL2R of your positive helicity soft graviton mode, and then this R, this is like a loop index, and it's just giving you some Laurent expansion in the other SL2. Okay? And so, yeah, so one of the key observations is that this algebra exists. So the upshot is that there's this this chiral algebra associated with the self-dual sector of gravity, and it's typically called the loop algebra of the wedge algebra of W1 plus infinity. There's some slight technicality about why that isn't technically true, and a more technically correct name would be the loop algebra of the Lie algebra of Hamiltonian vector fields in 2 dimensions. And so how do you see that this algebra is that loop algebra? Well, let me just pick some holomorphic coordinates on C2. There's a natural Poisson structure that I can give C2. And then I can just start writing down bases of Hamiltonian functions associated with that Poisson structure. And these guys are precisely, and then if I add a loop parameter, let me call it Z, a complex loop parameter into the game, these dudes, it's easy to see that under this Poisson bracket, they form precisely this algebra. Okay, so there are many interesting facts about these celestial chiral algebras. There's one for the self-dual sector of Yang-Mills theory as well, which is just the loop group of Lie algebra-valued polynomials on C2. As I said before, this L-ham C2 is closely related, although not literally equal to the loop group of the wedge algebra of little w1 plus infinity. Again, if you haven't drank the Kool-Aid, this little w1 plus infinity, this is a classical limit of, you should think of it as a classical limit of higher spin symmetry algebras that you get in 2-dimensional conformal field theories. But these chiral algebras can also be derived from asymptotic symmetries. They carry some natural action on hard or not soft gravitons in a scattering problem. And there's also a natural derivation of this algebra using twistor theory, which is something Laura also told us about a bit about this morning. And I'm not going to say any more about that right now, because in some sense I'm going to give you a more general version of that story later. So, okay, this all sounds like a great story, but one should always ask, why do we care about this? So one reason is, at least naively, you have these infinite dimensional algebras, and the generators of the algebra carry some action on hard degrees of freedom in your scattering problem. So these algebras can give you many constraints on scattering amplitudes, particularly in special helicity sectors. And that has enabled the bootstrap of some amplitudes using only the structure of these kind of 2-dimensional chiral algebras in both flat and curved spacetime that weren't known before. So, for instance, Costello has provided some explicit all-multiplicity expressions for 2-loop scattering amplitudes in massless QCD, which were not known before, using only the structure of these celestial chiral algebras. It also enables, in some helicity sectors, all-order collinear expansions of scattering amplitudes, which were not known before. And the structure of these chiral algebras admits some rich space of deformations when you start turning on background curvature. This is something that Giuseppe and Ben are going to tell us about later this week. And I should also point out, this is again something I know Laura mentioned this morning, that these celestial chiral algebras underpin the only known top-down constructions of asymptotically flat holography. So these constructions are cooked up in the arena of something called twisted holography, which is a holographic duality for topological strings on Calabi-Yau threefolds, and it makes them dual to some 2D chiral algebras. And yeah, these have been realized for, it's fair to say, quite exotic asymptotically flat spacetimes, but they're the only things we have, the only examples of concrete top-down constructions that we have so far. So these are the reasons why you should care about these celestial chiral algebras. They're important for many things. But what I'd like to talk about today is the following sort of mystery, which in the early days of this celestial holography program, when people were starting to talk about things like conformal primary wave functions, conformal soft theorems, everything was being done in general dimension. And then at some point, kind of like 4 or 5 years ago, people stopped talking about higher dimensions. And nowadays, everyone only talks about 4D. And on some level, there are like some very obvious reasons why that's the case. The conformal group in higher dimensions is, of course, finite dimensional. So in 4D, when the celestial sphere really is a 2-sphere, you have all the power of two-dimensional conformal field theory at your disposal, and you'll lose that if you go to higher dimensions. There's also this fact that if you talk to honest GR people, they'll tell you that the asymptotic symmetry algebra in higher dimensions should be finite dimensional. So you shouldn't have this BMS group that has infinite dimensional space of supertranslations in it. This is a little bit up for grabs because in some sense the existence or not of supertranslations is a matter of taste in terms of what boundary conditions you want to put on your gravitational field, but there are good reasons to put the boundary conditions that don't admit them. And also it's been shown that if you just look at soft theorems in dimension higher than 4, the symmetries associated with them are finite dimensional. So there are many reasons why people, I think, have stopped thinking about, or at least paused thinking about celestial holography in dimensions greater than 4, but for me at least, this is something that bothers me a little bit. Imagine if ADS-CFT was something that only worked in one set of dimensions. It wouldn't seem like such a robust or powerful statement. So I think this is something we should try to think about a little bit, and there are many ways to approach it, and the way I'd like to approach it today is just by saying, well, let me look for sectors of gauge theory and gravity in higher numbers of dimensions that have all the features I liked about the self-dual sector in 4 dimensions. And if you've, again, drank the right Kool-Aid, an answer should immediately spring to mind, which is whenever the number of space-time dimensions is an integer multiple of 4, there are classically integrable subsectors of gauge theory and gravity which have all the features that we like about the self-dual sector. And so what I'll tell you about today are these subsectors and the fact that they have chiral algebras associated to them. But the thing that's maybe slightly more surprising is that these are chiral algebras that still live on the 2 sphere. So in some sense, they don't have anything to do with the celestial sphere in a higher number of dimensions. Okay, so in the context of gravity, the subsector we have in mind here is what's called the hyperkähler sector. So if I have a manifold, let's say a complexified Riemannian manifold whose number of dimensions, complex dimension, is 4k, has some holomorphic metric g, we say that this manifold is hyperkähler if the holonomy of the metric is contained in the symplectic group SPK. All right, and that implies that the manifold, the metric is a solution of the vacuum Einstein equation. So why? Because SPK is a subgroup of SU2K, which means all of these guys are Calabi-Yau, which means that they're Ricci flat. Okay. So when k is equal to 1 and I'm in 4 dimensions, the hyperkähler condition is literally equivalent to vacuum self-duality. Okay? But this is some generalization to higher dimensions that are integer multiples of 4. And this condition on the holonomy means that hyperkähler manifolds admit something called a paraconformal structure, which is basically just this splitting of the tangent bundle into a tensor product of bundles, one of which is a flat SL2 bundle, and the other one is a rank 2K SPK bundle whose connection is non-trivial, and that connection, the curvature of that connection is the kind of SPK holonomy. So that means you can always write the metric in terms of, if you like, the symplectic form on SP1, or the natural SL2 invariant tensor, and the symplectic form on SPK, and then your field binds, which respect this decomposition of the tangent bundle. So just to give us something concrete to hold on to, let's think about the flat model, just C4K endowed with its natural hyperkähler structure. So what I do is I take my coordinates x1 up to x4k, and I can bundle them into this kind of quote-unquote spinorial representation that you may or may not be familiar with from 4D. This is just some 2 by 2k matrix that contains all the linear combinations of pairs of these coordinates that you need to reconstruct all the coordinates. And the flat metric is then just given by the natural SPK invariant measure on these z's and z twiddles. So I leave it as an exercise to the reader to check that this is true. Just write down the symplectic form in k dimensions, and use these expressions, whack them all together, and you'll see that miraculously this just simplifies to the complexified Euclidean metric. If I wanted to get R4K with its real hyperkähler structure, I just need to put some reality condition linking Z and Z twiddle. Okay. The hyperkähler, you might wonder, where is the hyperkähler structure lurking here? So this constraint on the holonomy, which is the definition I gave you of a hyperkähler manifold, is actually equivalent to the existence of 3 integrable complex structures on the manifold, which satisfy the quaternionic algebra. And that in turn is equivalent to the existence of 3 closed 2 forms. So that's, again, some sort of standard result in hyperkähler geometry. Okay, so now we change gears and we're going to use this magic wand called twistor theory. So I'll assume that no one in here has been exposed to this before. So what is a twistor space? Well, for our purposes, the twistor space, say, of this flat hyperkähler manifold, C4K, this is just an open subset of the 2K plus 1 dimensional complex projective space. And what open subset? Well, let me take some homogeneous coordinates on CP 2K plus 1. I choose to divvy these up into 2K coordinates that I call mu alpha dot. Remember, alpha dot now runs over 2K different values. And then 2 coordinates that I call lambda alpha. And they're equivalent up to an overall, we identify them up to overall projective rescaling. So if I take a Z and I multiply it by a non-vanishing complex number, that represents the same point in the complex projective space. And then the open subset that I remove is the subset, the subset that I remove from this complex projective space is the subvariety where all of these lambda alpha coordinates vanish simultaneously. So that's like removing CP2K minus 1 from this CP2K plus 1. And the fact that so this lambda alpha has 2 components, and we're saying they can't both be simultaneously vanishing, that means that we can treat lambda alpha like a homogeneous coordinate on the Riemann sphere. And that means that we get a holomorphic fibration of this twistor space over CP1, over the Riemann sphere. And explicitly, that's just you take your homogeneous coordinate and you just project it onto this lambda alpha piece. And by definition of this twistor space, those 2 complex numbers can't be simultaneously vanishing. So those are well-defined homogeneous coordinates on CP1. And there's also a natural holomorphic weighted Poisson structure on the fibers of this fibration, which is just given by taking the SPK invariant and contracting it into derivatives with respect to the coordinates on that fiber. Okay. So then the key result is an old one that was first proved by Penrose in the k equal 1 case, and then generalized by Simon Salomon in the k greater than 1 case, which says that there's a 1-to-1 correspondence between hyperkähler metrics and complex deformations of this flat twistor space. So what I mean by a complex deformation is that you take the tangent bundle of the twistor space, this has some Dolbeau operator acting on it, you deform this by a Beltrami differential, and you ask that the thing remain integrable so that it squares to 0. So you look for complex deformations of this twistor space which preserve the holomorphic fibration over the Riemann sphere and also don't mess up the Poisson structure on the fibers. And there's some other technical conditions. So this complex deformation needs to have a rational curve with a normal bundle of a specific sort, and that ensures that there's some nice correspondence between points in the hyperkähler metric and holomorphic rational curves in this twistor space, but we don't really need to worry about that too much today. So the upshot of this theorem from the perspective of trying to cook up some sort of celestial chiral algebra is that deformations of a hyperkähler manifold, or if you like, symmetries of the hyperkähler sector of general relativity, these just correspond to deformations of your twistor space which preserve this fibration over CP1 and the weighted Poisson structure, the fibers, on the fibers of that vibration. Okay? And now this is an easy problem to solve. So let's just take the flat model. So I want to understand what is the space of hyperkähler deformations of C4K equipped with its natural hyperkähler structure. So these things have to be Hamiltonian functions because we're preserving this Poisson bracket. They need to be homogeneous of degree 2, they need to be polynomial in the mu's, and they can be Laurent in the lambdas. So the reason why they can be Laurent in the lambdas is because we have this holomorphic fibration over CP1 that we're preserving. Okay. So then, it's in real money, all this means is that a generic deformation of the hyperkähler sector, you can always just expand it in terms of these modes. So you have some polynomial in the mu variables, which I should just think of as coordinates, holomorphic coordinates on the fibers of twistor space over CP1. And then I can have some kind of arbitrary power of lambda in the denominator. So we can label these things by a vector, say m in the 2k symmetric, in the 2k dimensional vector space of natural numbers, including 0, and the sum of these m's I'll call big M. And then it's very easy to see that these modes form a chiral algebra, which is just the loop algebra of the Lie algebra of Hamiltonian functions on C2k. And you can compute exactly what this algebra is. So it's a little more complicated than the one we saw earlier for k equal 1, but it's not that complicated. Okay. And there's a similar story for gauge theory. So in gauge theory, when you're in integer multiples of 4 dimensions, the field strength can be decomposed into irreducibles of SL2 and SPK. So I've written this decomposition here. So remember, epsilons are the symplectic forms. And the new thing, so if I was in 4 dimensions, I would just have the first 2 terms here. The thing you pick up in higher dimensions is this new thing we call F check or cap or something. And this is just because the anti-symmetric representation of SPK has non-trivial trace-free parts when k is greater than 1. Okay, and we say that a gauge field is what's called hyperholomorphic if the last 2 terms in this expansion vanish. So this is something that was written down in the 70s. Well, no, that's not fair. Early to mid 80s by Richard Ward and then by Ed Corrigan and friends, and then subsequently rediscovered by pure mathematicians in the late 90s. So the reason why pure mathematicians like this is that these hyperholomorphic bundles can be defined over any hyperkähler manifold. Here I'm just going to be talking about the flat model, C4K, but you can define them over any hyperkähler manifold. And it's also easy to show that if your bundle is hyperholomorphic, it automatically solves the Yang-Mills equations. So this hyperholomorphic sector really is a subsector of Yang-Mills theory. And again, there's this key result by Ward, which says that there's a one-to-one correspondence between these hyperholomorphic bundles and certain holomorphic bundles over twistor space. And then the upshot of this is that, yes?
I'm just struggling to see why the decomposition for 4K gauge theories is given by that. Is that a unique decomposition, or is there any? I mean, I don't see why it should just be those 3 terms.
Yeah. Okay. So it is unique. So the first term. This is skew symmetric in A and B, and that means if I trade these A and B indices for pairs of SL2 and SPK indices, it has to be skew symmetric under interchanges of these. And so it can be skew symmetric, say, on the undotted guys, and there's a unique skew object there, which is just the Levi-Civitas symbol. So that gives you this term. But then for it being skew symmetric on the dotted indices, it can be trace-free, in which case it has to be proportional to the symplectic form. Or it can have, it can be pure trace, in which case it has to be proportional to the symplectic form, or it can be trace-free, in which case it just gets bundled into this dude. Okay. So there's a lot, if by non-unique, what you mean is there's a lot lurking in here for generic K, that's absolutely true. Okay. But the decomposition into these irreducibles is unique. Okay. Does this answer your question?
Yes.
Uh-huh. Okay, so the upshot here is that if you want symmetries of the hyperholomorphic sector, all you have to do is look at deformations that preserve the structure of this theorem, basically. And again, these are Lie algebra valued functions on twistor space, which are homogeneous of weight 0. Again, they have to be polynomial in the coordinates on the fiber, and they have to be Laurent in the CP1 coordinates. And you can, again, just work out exactly what these guys are and what their chiral algebras. It's just the loop algebra of Lie algebra valued polynomials in 2K complex dimensions. Okay, so there's also a sort of dynamical story here where we can get these algebras from honest to God two-dimensional conformal field theories, there's this fact that the hyperkähler and hyperholomorphic sectors are described classically by classical two-dimensional conformal field theories, and then these chiral algebras are just encoded by operator product expansions in these CFTs. But the upshot of this is not for you to take away any kind of technical details, but more to emphasize that these really are algebras living in 2 dimensions on a Riemann surface. So who cares? If you take a step back, it's not terribly surprising that these classically integrable sectors of gauge theory and gravity have infinite dimensional symmetry algebras associated with them. What is surprising is that we can use the existence of these to start writing down things that are like higher dimensional analogs of maximal helicity violating scattering amplitude. So there are some higher dimensional versions of the Park-Taylor formula, if these words mean anything to you. It contrasts with general expectations from this celestial holography program, because the structure is still somehow a 2-dimensional CFT that's underlying it. And if there's anything I can try to impart for you to take away from this talk, it's the following, which is that I think it asks some questions about what we're really doing in this celestial holography program. Are we really doing holography on the sphere of null directions, or are we trying to do some sort of holography for certain integrable subsectors of gauge theory and gravity that have a twistor correspondence, and then we're doing holography on these twistor spheres that we always have this vibration over CP1. In 4 dimensions, the two coincide. But you should think of this as an accident, not something that's true in general numbers of dimensions. Okay, so there's lots to do. I don't have anything to say about any of these yet. Like what connection, if any, these chiral algebras have with what you might call conformal primary wave functions, or with soft and collinear limits. There should be some sort of link with asymptotic symmetries, but I don't know what it is. And most interestingly, at least from my perspective, are there top-down manifestations of this? So is there some higher dimensional version of the twisted holography program that's really something about hyperkähler geometry? And again, I don't have anything precise to say about that, but thanks for your attention, and stay tuned for lots of other interesting things throughout the week. Thanks.
We have time for a couple of questions.
Thanks for a nice talk. I was tantalized by your last remark that you have some kind of a higher dimensional version of Park-Taylor amplitudes. Do they sort of take a natural form as compared to the 4 dimensions is one question, and the other is?
Written in a correct way, they're like almost, the formulae look the same as the 4-dimensional ones. And part of the reason for this is the following. So I swept this under the rug, but let's take the gauge theory story. This hyperholomorphic sector is defined by some vanishing of these invariants. Where do we? These guys. If you actually count how many equations this is, it overdetermines the gauge potential. Only in 4 dimensions does this not overdetermine the gauge potential. So but although these are overdetermined equations, they still have interesting solutions. I mean, you can use this twistor construction to generate them. And what this translates to in the scattering problem is that the kind of momenta that hyperholomorphic gluons, for instance, carry is not a general null momentum. So if you were injected with spinor helicity at a young age, you know that in 4 dimensions, a null momentum is just a pair of SL2 spinors. And in 4K dimensions, a pair of spinors, one that's SL2 and one that's SPK, is also null, but not every null vector can be written in this way. So somehow the hyperholomorphic guys have to have momenta that can be written in this way, and this has some non-trivial codimension. But because you write them in this way, there is an SL2 spinor associated to them, and that means you can have things like angle brackets, like you have in the Park-Taylor formula.
Yeah, interesting. Thanks.
Thanks. Can I ask a slightly tangential? I was just curious, what would happen in like 2K dimensions if like K is odd, like in 60? because I guess you don't have the hyperkähler structure anymore, but you can still have sort of self-dual things. Can you have infinite algebras there?
Okay, so you can have self-dual,
Other stuff.
higher forms, but not self-dual gauge fields
Yes.
or gravitons. So something you could, and I should advertise that people thought about this again in the 80s and 90s. So in 4D, you can take symmetry reductions of the self-duality equations. And if you symmetry reduce the self-duality equations to 3D, you get the Bogomolny monopole equations. And if you symmetry reduce them to 2D, you get Hitchin's equations. And so in 2K dimensions, what you can imagine is you get some higher dimensional version of Hitchin's equations. And this is something that integrability people looked at, but somehow it's not quite as interesting as the 4 down to 2 example. So one reason why maybe we haven't all learned about hyperholomorphic gauge bundles is because there are no finite action solutions to the Yang-Mills equations in dimension greater than 4. So although these are interesting field configurations, they don't give you kind of topological invariance the way that Yang-Mills instantons do in 4 dimensions. And that means that their symmetry reductions will similarly lack some of the kind of topological richness that we associate with symmetry reductions of the self-dual equations in 4 dimensions. I don't know if this is really answering your...
One more very quick. Can you also do like curved backgrounds, like simple ADs?
Yeah, so the idea would be that, in principle, the idea would be that anything we can do for the self-dual sector in 4D, we should be able to do for the hyperkähler or hyperholomorphic sector in higher numbers of dimensions, but solving the integrability constraints in a non-trivial way on the twistor space can become slightly more non-trivial. I say yes, but I have nothing to point to demonstrate this for you.
Okay, so maybe can we postpone more questions for
Yeah.
later? Thank you. So let's thank Tim again.